So, well, it's a great pleasure to be here. So, first of all, I would like to thank the organizers for this very kind invitation. And so they told me that I should give a colloquium that's let's say a broad field. So I'm going to talk about quantum simulation. And so I see that there are some experts in the audience. I'm sorry about them because what I'm going to tell them, will not be anything new. But anyway, so I hope that at least, a couple of things, will be new for them. Well, during the last few years, we have experienced experimental breakthroughs in many fields, and in particular in trying to get control over the microscopic world. So people are able now to isolate a single atom, or two atoms, or few atoms, or ions, or photons, electrons, some superconducting currents, and so on. And as you probably know, so we managed to control these systems at the very small level and at the quantum level. Then there are some people who have found some applications for that. And so in particular, we would be able to control those systems and to make them interact at will, as we want. Then we could build computers that could be much faster on some specific problems than any other computer that exists right now. Or we could build some other communication systems that would be secure and under eavesdropping, or some sensing devices which would be better than the ones that are existing. But I'm not going to talk about that. I'm going to talk about a different application that may come out from this control over these systems, and that's the field of quantum simulation, which was already identified by Richard Feynman in 1981 as one with a major problem in general in quantum physics. So he realized that whenever we have a quantum many-body physics, as they appear in chemistry, or they appear in material science, or they appear in high-energy physics, then it's very hard to to make physical predictions with those systems. And basically the reason is that even if we use the most powerful computers, then the computational time in order to get an answer to any particular physical question on the systems will grow exponentially with the volume of your system or the number of particles. So this limits ourselves, at least if we want to do exact calculations, to very small systems. And in fact, so in his paper, then he says very clearly that if you want to make a simulation of nature, you would better make it quantum mechanical. So what he says that indeed the problem of this exponential growth lies in the fact that you're trying to talk about quantum physical properties, and you're using a classical computer which cannot deal with superposition itself. So you want to really simulate and make predictions about a quantum system, then you should use a quantum system itself, a quantum computer or a quantum device, which could use superpositions. At the time, this idea, I think, that was not so much followed, but 5 years after that, or 4 years after that, so the first ideas about quantum computation came up. And in fact, if you read carefully this paper, most of the ideas of quantum computation were behind that. So he proposed that in order to simulate quantum field theories, then what you do is to discretize space, to discretize time, and to make some kind of evolution in time just by taking this discretization in space and doing like what we will call today 2-qubit gate. So he describes a quantum computer in his paper. But as I mentioned, so this was a little bit left out until the 90s, when people started talking about quantum computers and maybe trying to build a quantum computer. So, of course, one of the main applications of a quantum computer would be exactly the problem that we was mentioning in this paper, so to solve this kind of problems. So a quantum computer, according to what I know so far, it's very far away, so it will take a very long time to build a quantum computer. But it may still be possible to build some other devices which can solve this problem without the need of building a quantum computer. And that's the field of quantum simulation that I'm going to talk about here. So, so that's the outline of my talk. So first, I will make a very simple statements why these many-body problems, and in particular quantum many-body problems, are difficult. So this exponential growth of the computational time or the memory or whatever, can be very easily explained. So I'll do it here, and then I will motivate then quantum simulation. So to use a quantum device if you want to solve quantum physical problems. So I will formalize that a little bit. And then I'll concentrate on one particular incarnation of a quantum simulator, which is pursued in several places around the world, here as well, in Paris as well, which are atoms in optical lattices. And I will briefly mention So how to simulate condensed matter physics problems and high energy physics problems with these atoms in optical lattice. And at the end, I will go into something more specific to the work that I'm doing right now, and I'll talk about a way of building these quantum simulators now using not atoms in optical lattices, but atoms close to dielectric materials, and in particular to photonic crystals. So this is a work that we did together with Alejandro González Tudela, who is a postdoc in our group in Munich, Chenlong Huang, who is now in Purdue University, Derek Chang, who is in Barcelona, and Jeff Kimball, who is in Caltech. Okay, so I'll start very, very simple. So how hard are quantum many-body problems? And so let's consider a problem that may appear very naturally in physics. So you have a piece of material and you like to describe it. And so typically, we don't describe starting from first principles. So we don't take the standard model to model this and solve it, but rather we make phenomenological models to describe the physics of this system. So for example, if you're interested in the electrical properties, then you can make a model. You see that your system, you have maybe is composed of materials composed of atoms, and electrons are moving in these atoms. So what you make a lattice model, like representing the lattice of the atoms that are in the solid, and the electron is moving there. So you have models at the end which look somehow like this. Oops, I'm sorry. So like this on a lattice. And so since we have some ideas about the interactions here, so we write typically some Hamiltonians which should describe the physics of the system. And so we are asking questions like, so what is the physics of dynamics or thermal equilibrium? So for example, you would like to know what happens if you cool down your material at very low temperature, what would be the physics? And so we would like then to, maybe to solve the problem, to compute what is the ground state of your Hamiltonian, which would correspond to the zero temperature behavior of your system, and indeed to check that maybe your phenomenological model coincides or gives the same prediction as what you measure in the lab, and maybe after you have checked that your model indeed represents the physics of your system, then you can start changing the parameters and making predictions about what will happen with your system. Actually, the fact that this is a difficult problem, so to solve these model Hamiltonians themselves, it's very difficult. And you can see it even in a classical system. So imagine that we make the simplest model which could correspond to classical spins. So we, for example, want to represent the magnetic properties of your material. And we make a lattice models in which in each lattice side or in each lattice vertex there is a spin which can point up or point down. Let's say one is up and 0 is down. And imagine that somebody gives you the Hamiltonian, which in the classical context, it tells you what is the energy of each configuration. So for example, it tells you that the energy of a configuration can be written as the energy of every pair, or every nearest neighbor pairs. Like for example here, there is some energy associated to having these two spins in different directions and some energy in the same direction. So somebody gives you this information, gives you the model, and you would like to know what is the ground state of the systems, or namely, what is the configuration which minimizes the energy, for which the energy is the lowest one. And one way of solving that is to start with the configuration with all the spins are down, 0, 0, 0, and you compute the energy. Then you take the configuration in which the last one is 1, and then you compute the energy, and then you go all over possible configurations. You make all these computations, you look at your list, and you find that 1 has the lowest value of the energy, and then you say, oh, this is the configuration corresponding to the 0 temperature. And of course, this is a very naive way of doing that. And in fact, you see that the number of computations that you will have to do in order to find what is the solution to your problem will be at least as many as configurations you have. And since there are 2 to the power n configurations, then it means that the computational time to do that will grow exponentially with the number of spins that you have on your system. One could say that, that's a very naive way of finding that, of finding the lowest energy. And in fact, so for example, if I have some configuration and I change one spin, then I don't have to compute the energy from the beginning, but just the energy in which this spin is involved. But still, for each configuration, I will have to do at least one computation. So there will be, as number of computations will be also exponential with the number of particles. And so this means that in practice, you cannot solve these problems when n is of the order of 100 or so. Of course, now, if somebody gives some extra information in this classical problem, it tells you, oh, there is some symmetry. Imagine that my system is homogeneous. So these energy functions do not depend on the site on where you apply. They are always the same. then the problem becomes very simple. So it's, in fact, so you have something like ferromagnetic interactions, doesn't matter what it is, then you can just right away find out that either this one or this one here should be the one that lowers the energy. So the computational time, I mean, it's basically constant. I mean, you don't need, it does not even grow with the system. So this example shows you two things. So first of all, that classical systems in general are very difficult to simulate if you want to solve these properties like finding lowest energy configuration, zero temperature behavior. And in fact, one can even prove it mathematically. The fact that this problem is in a class of computational problems, which I'll call NP-hard, for which, so I mean, should take an exponential time. There is no, whatever you think about them, I mean, they should take an exponential time in full generality. However, you have some symmetries that they often appear in nature, then you can solve it much easily. Now, like the case that I gave here. Okay, so let's move to the quantum case. And so we have another model, and the model is given by a Hamiltonian, and we would like to find what is the spin configuration at t equals 0. And unless the spins don't interact with each other, if we have spins, then the configuration that will be the ground state of the system will be a linear superposition of all possible configurations. So it's a quantum system, and if there are interactions, then we'll have the ground state will be just some state on this huge Hilbert space, so it will be a linear superposition. So in order to describe what is the solution to my problem, in principle, I should tell you what are the coefficients of this linear superposition. But since there are 2 to the n configurations, there are 2 to the n coefficients that I have to give you, complex coefficients that I have to give you in order to tell you what is the solution. So not even to calculate, just to give you, to tell you what is the solution, I will need 2 to the power n coefficients. And if I want to do a calculation, then I will have to compute these 2 to the n coefficients. So the number of computations that I will have to do, in any case, will have to be at least as many as the coefficient that I have to give you. So it will be 2 to the power n. So this is why there is also an exponential dependence of the time, and in this case, even of the memory of your computer with the size of your system. And so what it says is that the quantum problems, apart from the difficulties of classical problems of finding the configuration, even the description of the configuration, it's exponentially difficult. So it gives you an exponential law. And that's, you can see, because it will be in general a superposition. So you just think about number of spins, and you want to store these coefficients and these complex numbers with certain accuracy in a computer, then you see that for 10 spins you need 128 bytes, but you go to something like 100 spins and you will need 10 to the 29 bytes or 500 spins, so a reasonable number of bytes. So this limits exact computation with this kind of problems for ground states or even for dynamics to very few systems. So you do dynamics, so typically you can work with 20 spins, but not more, 22 maybe. And if you look at ground states, then you can use tricks like in Langsos and maybe a couple of symmetries in order to reduce, and I mean the record on exact calculations now with certain symmetries of the order of 40 spins. And so unlike the case of the classical systems, if I tell you that your system has certain symmetries, it doesn't help much. So the fact that your system is homogeneous will not reduce the number of coefficients. So one can see that let's say the dimension of the Hilbert space of symmetric states, so the ones that has translational invariant states of homogeneous state, still has a dimension which is 2 to the power n divided by n. So you gain just a factor of 1 over n, so it's still exponential. So this means that the quantum problem, in general, in full generality, even if you have symmetries, may be very difficult, and so this is why you're limited to a very few number of particles. Okay, so one may think that maybe these superpositions are not important in physics, but indeed they are very important, and there are many problems in physics where these superpositions are required to explain the physics of these problems. And so, I mean, the superpositions are important, so these problems are important, although in some cases there are theoretical techniques which can overcome these problems. So for example, there are some problems for which you can use quantum Monte Carlo methods, and quantum Monte Carlo methods work and give you the solution in a very efficient time. And there are some approximations, mean field theories, which in some conditions they also work, etc., etc. But you say that there are many problems for which it's not known a technique, or there are not techniques such that we can solve these models. And this is where this kind of quantum simulation comes in to help. And so the idea is what I mentioned before was just in this paper of Feynman. And the idea that he was posing in the paper is that if at the end I have to give you the solution in terms of a superposition, instead of writing in a classical computer, instead of storing my coefficients of my system, let's take a quantum system and let's prepare it in this superposition. So if I have a quantum system, this will be my quantum simulator, and I'm able to prepare my system in this particular superposition, then I will require n qubits in order to store my state, no? Because there will be superposition of these n qubits, what I will have, and not 2 to the n, let's say, classical qubits as I would require in a classical computer. So the idea of a quantum simulator, then it's very simple. So you have a problem, a model that you want to solve, and this model could be, a chemistry molecule or a material problem, some model describing electricity or conduction or magnetism, or some high energy physics problem. And then let's take another system. This will be your quantum simulator, which has nothing to do with the original problem that you want to solve. This is something that you can have in your lab, that you can control, and engineer the interactions in your quantum simulator in such a way that the dynamics of your system is described exactly by the Hamiltonian that you want to solve. And if this is true, then what you can do is just perform your experiment here. Just prepare the superposition. For example, you want to compute dynamics, just let your system evolve according to this Hamiltonian. So the superposition will be stored in your system without having to store coefficients. And then if you want to make a prediction about a physical property, measure it in your quantum simulator. You want to know what is the magnetization, measure the magnetization. You want to know correlation functions, measure correlation functions in your quantum simulators. And it's very simple to show that this overcomes, for many problems, the obstacle that was originally pointed out by Feynman. So actually, these quantum simulators is not an abstract idea. People are building them in the labs. And so I've been very much working on 2 kinds of systems, so cold atoms in optical lattice, so trapped ions. But there are many other systems in which people are building these quantum simulators. And so here I will concentrate on cold atoms in optical lattices. And okay, so, well, you know this very well, being one of the centers of the world in atomic physics at ENS. So you know that during the last years, people have been able to control atoms to a degree that is really incredible. So you're able to cool atoms, you're able to trap atoms, you're able to trap single atoms, 2 atoms, few atoms, to make them interact, to change the interactions properties between the atoms. And of course, then this is one very nice playback for this field of quantum simulation. And one way of doing this quantum simulation is to use what is called optical lattices. And so the basic idea is to now trap these atoms, to make them levitate in space just by pushing them with lasers. So what you can do is to take counter-propagating lasers in such a way that they form an intensity standing wave pattern, interference pattern. So there's like a periodic structure like this one here. And then if these atoms see this laser of resonance, then they behave like small dipoles that are pushed, electric dipoles that are pushed by the electric field of the lasers. So they push them to some regions, so the regions of maximum or minimum intensity. And that's a way in which you can trap these atoms in optical lattices. And now these atoms in optical lattices, if they are very low temperature, then they will be in the first Bloch band. And if they're in the first Bloch band, they still can jump from one place to another, so they can tunnel from one place to another one, and they can also interact if they meet at some particular place. So the physics of atoms that are trapped in optical lattices at very low temperatures is described by something that is called the Bose-Hubbard model, if these atoms are bosons, or the Fermi-Hubbard model in the case of these are fermions. So in a very naive way, one could say that if you put atoms in optical lattices, then you could simulate the Bose or Fermi-Hubbard models, and in fact you were able to tune the corresponding energies associated to the process of tunneling, this T, and the process of the interaction, this U, just with external parameters. And in fact, this experiment took place in 2001, and after that there have been many experiments where, for example, people were able to observe the physics related to this Hubbard model, namely that if changing the ratio between T and U, you can go from one phase, which is superfluid, to some other phase, which is a Mott insulator. But if you're able to do that, so you're able really to put your atoms and control the parameters that you have in your system, you can start playing now with some of the degrees of freedom. So these atoms, apart from moving, they have some internal structure, so they have some spin, and this spin can be also used. And so now you can have, for example, that atoms are just moving in this lattice with spin up and spin out, and they interact with each other. And if you just write down what is the model that describes that, then you come with the Hubbard model, which is one of the basic models that appears in condensed matter physics. So in fact, now you take into account the possibility that you have different internal states in the atoms, and maybe this you can tune also these parameters t and u. You can make maybe the t complex and so on. Then there is a variety of models that you could simulate that are of interest in solid state physics or in condensed matter physics, which are called Hubbard models. And in fact, some of these models cannot be solved with any computers, and so that's why people are interested in building these, let's say, quantum simulators in order to solve problems related to electrical conductivity and to these Hubbard models. So you can also now, you are able to fix one atom per lattice site, so to allow them only to tunnel virtually, so that most of the time you have one atom per site. Then you can still have the spin degree of freedom, so you can have a configuration where you have a lattice of atoms, and in each of the lattice sites there is a spin, which could be, for example, spin up and spin down. And now these atoms, if you control with external parameters, can make them also to change the interaction properties, and in this way design spin Hamiltonians like the ones that I mentioned before. And so that's also useful to study spin models, magnetism, and there's plenty of problems that people cannot solve with classical computers related to exotic magnetic materials that could, in principle, be solved with these systems. So that's something that was known already for a very long ago. So what is a little bit newer is the possibility of also simulating, at least in theory, high-energy physics models. And in high-energy physics, of course, it's a bit different from condensed matter physics because of different reasons. So first of all, in high-energy physics, you have matter and gauge fields. So as you know, the matter is represented by fermionic fields, and the gauge fields are bosonic fields. So you have to have fermionics and bosonic degrees of freedom from your system. Apart from that, the high-energy physics models are relativistic theories. And so in principle, one should think that one should be able to move your quantum simulator at relativistic speeds, but actually this is not required. And on the other hand, they are gauge invariant, so meaning that they have some local symmetries. So you write a Hamiltonian formulation of your quantum field theory, it means that there would be some local unitary operations that would commute with your Hamiltonian. And this fact that your Hamiltonian commutes with some local operators means that there are some conserved quantities which gives rise to Gauss' law. Okay, so that's some ingredients which are very peculiar from high-energy physics. But already some years ago, so Kogut and Susskind, they wrote, for this quantum for high-energy physics model, a lattice way of describing them, and in terms of a Hamiltonian formulation. So in high-energy physics, you typically work with actions because you want to see explicitly Lorentz invariant, but then they wrote a lattice formulation, a Hamiltonian formulation for that, in which basically that's a kind of a cartoon scheme. So they say that if you give me a theory like could be quantum electrodynamics or QCD or any other quantum field theory, that in principle you can discretize a space in the same way as Feynman was saying. And you can, for example, put the fermionic degrees of freedom in the vertices of your lattice, the bosonic degrees of freedom in the edges of your lattice. And now any Hamiltonian describing high-energy physics can be written as three parts. So first of all, there is a Hamiltonian which describes the matter itself, which is very similar. So it's a Hamiltonian which is acting only on the fermionic degrees of freedom that you have in your edges. So for example, you may think that you can have fermions, let's say maybe with a spin up, spin down in these edges, and so there would be some Hamiltonian which will tell you maybe if you have some different energy, if you have a spin up or spin down. And then there would be another part which would be the bosonic part. So this is here, for example. So each of the edges, this would be a part of your Hamiltonian, and this would describe, for example, the electric energy. You have QED, then the Hamiltonian, the energy, contains an electric and a magnetic energy. So this would correspond now to the electric energy of your bosonic degrees of freedom or your electromagnetic field. And then there would be another term, which would be a plaquette term, that would describe the magnetic energy, let's say, or your field theory. And then, apart from having the fermionic and bosonic degrees of freedom and the corresponding Hamiltonians, then you will have also some interaction and this interaction will involve, so like it's shown here, nearest neighbor fermions and the bosonic degrees of freedom that are outside. So typically, if you give me a model that in a quantum field theory in the continuum, then you can discretize it, and then you can write, in many cases at least, like QCD or QED, in this particular way. So at the end, what you have is a lattice Hamiltonian. So it's I mean, you can write down some Hamiltonian that is very much like the ones that appear in condensed matter physics, this Hubbard model that we had before, with a couple of differences. So the first difference is that you have fermions and bosons. The second is that you have these plaquette terms. So this is like a four-body interaction that appears there. And the other one is that you have these, fermions and interacting with the bosons here, and one of these links. And the other one is that your Hamiltonian, this gauge symmetries, is just represented here by the fact that there is a unitary transformation that acts on each of these crosses, so acting on these bosonic degrees of freedom and the fermionic degree of freedom, which leaves your Hamiltonian invariant. So these are local symmetries. So in other words, so in principle, you can write, if you want to solve a high energy physics problem, then you can write it in this way. Of course, you will have to take the lattice to 0. You will have to do renormalization. I mean, everything that we know from quantum field theory, but you can do it in this way just by doing different experiments corresponding to different lattice sites. And at the end, you would be able to get the solution to your problem. So with cold atoms, so actually, I mean, we and some other people figure out so how to simulate these different models with, this gauge symmetry is characterized by a group, a symmetry group, a gauge group that can be abelian, non-abelian. So for the different setups, so we thought several ways. And so I don't want to enter into the details here, so maybe because I want to talk about the other part, but just the fact here is that at the end you want to have this gauge symmetry. So you won't like to have this local symmetry. So how do you manage that? So first of all, you will have to have the fermions, and the fermions would be fermionic atoms. Okay, and it's clear that you have to have fermions, and these fermions should be able to hop in your lattice. Okay, and that's something that is already in this optical lattice. And on the other hand, you have to have these bosons, and these would be bosonic atoms themselves that have to be in the links. And one way of realizing that is to put, like it's represented here, so a lattice that is displaced with respect to the other one by half a wavelength, and to trap in one lattice the bosons and in the other one lattice the fermions in such a way that indeed the bosons are in the links with respect to the other lattice. And now the interactions, so whenever a fermion hops from one side to the next one, it has to change the degrees of freedom of the bosons, and this would be just collision, fermion boson, so that comes right away. A collision can make one fermion to hop from one place to another one, and maybe the bosons that are in between, if they have two internal states, they can flip the internal state at the same time. And it turns out that in this collision, which makes this interaction between the fermions and the bosons, the collision, if it conserves angular momentum, this is reflected in the theory in the gauge symmetry. So you can map this local symmetry that is required in high energy physics to a local symmetry in the interaction that appears in atomic systems, which is angular momentum conservation. And actually, you can do this for different models. So we have done it for U1 symmetries, for SU2 symmetries, and so on. And so you can work with that. The difficult part here, experimentally, there are many difficult parts. So first of all, you have to put fermions and bosons at the same time. You have to engineer the interactions and so on. But maybe the most difficult part is going to higher dimensions, so to go to 2 dimensions or to go to 3 spatial dimensions. And the reason is not because of these interactions, which are always the same, but rather because of these plaquette terms. So these plaquette terms, which corresponds to the magnetic field, this will require 4-body interactions, whereas in atomic systems, naturally, we have 2-body interactions. So you have to get out of 2-body interactions, 4-body interactions, and the only way, I will explain a different way, but one way of doing that, which is very naive, is to use 4th-order perturbation theory. So you have 2-body interactions, and you have a particle which interacts first with one, then the other one in a 4th-order process, then you will have an effective Hamiltonian, which has 4-body interaction. And since the original Hamiltonian has the right symmetries, is gauge symmetric because conservation of angular momentum, then you know that in all perturbation orders you will still keep this gauge symmetry. So at least there are ways of thinking about that. So that's in theory. In practice, of course, you have to rely on a 4th-order perturbation problem to simulate your system. That's going to be very tough. So this is why I talk about some way around it. But Okay, so I think that there are some people in Heidelberg, and I don't know if some other places, which are starting doing these experiments to try to simulate Schwinger models. This is one dimension, 1 + 1 dimension QED. And so I guess that the first experiments, I mean, at least showing the basic concepts that appear in high energy physics, like confinement, string tensions, string breaking, and so on, may appear in those experiments soon. Going to 2 dimensions, as I mentioned, will be probably much harder. Okay, so what are the bottlenecks, or some of the bottlenecks of these experiments to put it into practice, some of these models? So if you look at the literature, so people have simulated both Hubbard models, simulated some spin systems, they have simulated, experiments here and so on. Something that has not been reached so far is, for example, this Hubbard model and with fermions, or these high energy models. And one of the reasons is that even though these experiments with cold atoms are extremely cold, are nanokelvin temperatures, they are not cold enough because the temperature has to be smaller than the energy scales that you have in the problem, that this T and the U or the J's that appear in these Hubbard Hamiltonians, and that's relatively tough. And so one of the goals of the atomic physics experiments working with atoms in optical lattices is either to lower the temperatures or to increase the energy scales. And that's why people are working now with Rydberg atoms, polar molecules, and some other setups in order to overcome this problem. And I'll show you about some other possibility, which is a work that, as I mentioned, that's been done together with this gentleman. And so that's a quantum simulation with atoms and photonic crystals. Okay, so now I'm changing a little bit topic. I'm going to talk about photonic crystals, dielectric, and atoms that are close to them. And again, so you look at the experiments that have been carried out during the last 3-4 years in this particular field of quantum nanophotonics. I mean, they have been really very extraordinary. So people are able not only to trap a single atom, but they're able to put it close to a dielectric waveguide, also some optical fiber where you can send light. And you can also put it close to some surfaces that are dielectric. And now you can nanofabricate these surfaces in such a way that they get a periodic structure. Like, for example, here. That's an experiment in the laboratory of Jeff Kimball, in which he takes some dielectric material, and so he nanofabricates some structure which is periodic. So this means that now the light that is propagating in this dielectric will have some band structure. So the modes that are inside the dielectric will have some band structure. So there will be some band gaps where the light cannot propagate, and then will be some other frequencies of light which can propagate very well. And now you can couple the atoms, so you can put the atoms very close in such a way that the evanescent wave that is coming out of the dielectric of the propagating mode is talking to the atoms, and then these atoms can have very strong interactions with this light. So for example, they can emit, you can excite the atom externally, and now they can emit a photon, and this photon, since there is a big coupling, is coupled to the fiber, and then it's going out. So it's a way of coupling very strongly systems with the fibers. So people have demonstrated already, I think, that Purcell effects, which is a figure of merit that measures what's the probability that your atom is coupled to the fiber rather than to the external world of the order of 10 or so, but there are promises of going to factors of 1,000 or 10,000 even. So there are many experiments even with plasmons, so with metallic surfaces. And so this brings maybe the possibility of now simulating Hubbard models or the spin models just by trapping atoms, making them levitate close to some dielectric structures that you can nanofabricate, and maybe in this way to overcome some of the problems that I told you before, and that's what I want to talk about. So let me first go to Hubbard models. And so remind you, so I was telling you that these Hubbard models, so physically they're represented by atoms that are trapped in some periodic potential, and that they can tunnel, and that they interact if they meet at some particular place. And I mentioned that there are some energy scales related to these two processes. So one is the tunneling. So it's like kind of a kinetic energy of the motion of these particles. And this kinetic energy is measured in terms of a parameter that is called T, has energy, units of energy. And the other one is this interaction energy. So what is the energy when two atoms meet at a particular site? And that's U. And as I mentioned, the Hamiltonian that you write can be written in terms of these two parameters. And now in these atoms in optical lattices, actually these two parameters can be changed just by increasing the intensity of your potential. Then you make the barriers higher so the atoms can tunnel less. So this T goes down and they get more concentrated to the U goes up, so the interaction energy goes up. However, there is an upper limit, so you cannot just tune these parameters at will. And there are several limits, but the most clear one is that these two, t and u, are limited by h squared divided by m times d squared, where d is the distance. And that's very simple to understand. So you take two lattice sites. Somehow the energy, you want to have tunneling, then your wave function has to be spread among the two sides, and the kinetic energy related to this distance will be exactly h squared divided by md squared. And you can easily show that this t cannot be larger than this energy. So, and the same thing happens with this u. So if you want to increase t and u, the energy scales of your system, instead of lowering the temperature, then what you will have to do is to increase this parameter here, this what we call recoil energy, because this distance in this is related to the wavelength. So one way of recoiling of increasing the recoil energy, so this energy, is to choose a lower mass, a lighter atom. And that's why some of the people are doing experiments with lithium instead of rubidium or sodium, because lithium is lighter, and then these energy scales go up. But another way would be to decrease d, right? Decrease the distance between the atoms. So I told you that these lattices are made out of light, optical light. So in principle, the wavelength of light, if it's an optical, cannot be changed. So what I'm going to talk about is a way of changing this distance, of making this distance smaller. And so during the last years, we have been thinking about ways of doing that. So these are two early attempts. So one was together with these people, with Peter Zoller and Michel Looking, in which we thought of using now metallic nanospheres in such a way that these atoms would couple to the plasmons that are in these metallic nanospheres. They will experience very strong electric fields, very strong gradients of electric fields, and then you could trap the atoms with these strong electric fields. And so in principle, this is possible. These are dissipative systems, very dissipative systems, so the sphere will heat up, and so that's a problem, but still I think that there are people trying to do experiments. We had even a more crazy idea, which was to create in a 2D plane, 2D metal, of a superconducting device, of a type 2 superconducting device, to pin vortices with some magnetic fields in such a way that now at the vortices there is a very strong magnetic field gradient. And so in each of the vortices you will have a gradient, and if you choose the fields properly, then it turns out that you can have a minimum where the atoms that behave, or they also have a magnetic moment, could be trapped. And so in this way you could have trapping of atoms at a distance and lattices which are of the order of, let's say, 50, 100 nanometers. Of course, that's a very tough experiment. It's of course, when you start just putting things close to surfaces, there's a lot of physics going on that has to be investigated. But anyway, I understood that people are doing experiments starting with dielectric, not with atoms, but with small dielectric spheres to try to trap them inside vortices, maybe a first step. But I want to talk about here photonic crystals. And so the idea that with photonic crystals this can help, it's very clear. So you probably learn in your studies that if you have light propagating in a dielectric, then the period of, and you have a standing wave, then the period of the standing wave, a spatial period, is decreased by the factor which is the index of refraction. So you have any optical light, and then you put a dielectric material, then here you have an oscillation which would be closer. And of course you cannot, this will happen inside the material, so you will not be able to put the atom there inside the material, but there is always some evanescent wave, and one can easily show that this evanescent wave gets also the same period. So in principle you could trap these atoms on top of this evanescent wave, and now the distance between your atoms will be decreased by a factor of the index of refraction. So for example, if the index of refraction is 3, then the distance decreases by a factor of 3. So the energy scale will be increased by a factor of 9. That will be a cheap way of doing that. But maybe, we thought that in principle could do much better if you nanofabricate systems, because then, for example, imagine you take a dielectric material and you drill holes that are separated by very small distance, let's say by few nanometers. And if you put light on them, then if you look at the intensity profile of the light, it has to reflect somehow the structure that you have here. So in other words, the intensity of light, so in some places will have to be maximum, and maybe in the middle of these holes will have to be minimum and maximum. So it has to be an oscillation which has to have a period that is the one in which you drill the holes. And since you can drill the holes maybe very close to each other, then in principle you should have a pattern also of a standing wave that also has a distance between minima that is of the order of the distance of or the same as the distance that what you drill. So in fact, I mean, the people who are working with nano optics will realize right away that this is true. However, the visibility, so the contrast of this oscillation decreases exponentially with the distance of your system. So this means that you will have to trap the atoms very close to the crystal. So if this distance is of the order of 50 nanometers, then you have to put your atoms at 50 nanometers at most away, in such a way that they see this intensity. But if you put atoms 50 nanometers of a dielectric, then the atoms realize that the electric is made out of atoms themselves, so the atoms start talking to each other, and then they have the coherence process and some other processes that maybe you don't want. And in particular, there are some forces, so van der Waals forces or CASIMIR-POLDER forces, which will attract the atoms towards the material, and probably your atom will get stick to the material. Okay, this is true. So in principle, one could think of pushing the atoms away with lasers. So you just put a laser that is pushing them away from the material. But if you do a back of the envelope calculation, so what is the intensity of the lasers that you need in order to push the atoms away from the material, just to keep them levitating close to the electric, they're really very, very high. So I don't give you the numbers. So, but still, I mean, so what one can do is to take advantage of these CASIMIR-POLDER forces as follows. So these CASIMIR-POLDER forces, as I mentioned, so these are like interactions, like dipole-dipole interactions, van der Waals interactions between the dielectric, the atoms that compose your dielectric and your atom yourself. Then they are attractive. And so if I put an atom close to a dielectric, then it will come to the atom. Now, if I have a rod like this one here, then it will also be attracted by the atom. But you see that if I put it a little bit away, then it will be attracted in this direction. And if I put it in this direction, it will attract in this direction. So the CASIMIR-POLDER forces will attract it. So we'll have some force that is going towards the position of the rod. And at the same time, it will go down. So if we now use push light only in this direction, so one can combine the action of the laser light pushing and counteracting the force of this dielectric together with the force that you get from CASIMIR-POLDER forces, and there are some equilibrium positions where you could trap the atoms. And so that's what we have been studying. So we did some real calculations with realistic materials. And so just to give you some numbers, then if you take rods which are separated by 50 nanometers, like the ones drawn here, and which have a radius which is only like 10 nanometers or diameters of the order of 20 nanometers, and heights of 110 or 120 nanometers, and you use the wavelengths for rubidium atoms, and then you will have some potential, and that's what is described here along the Z direction, along the Y direction. If you push them with a laser, and that's the intensity that you will need in order to push your systems, and that's a very high intensity, is measured in terms of radio frequency. But according to what I learned from my collaborators, experimental collaborators, this will not burn your material. So in principle, it should be possible. So the idea is that indeed, I mean, maybe possible. I mean, this is something that Jeff Kimball is not scandalized, at least. And so that we could do experiments in such a way that one could trap these atoms close to these surfaces. And in that case, so one would gain a factor of basically 100 in the energy scales of your system. So, of course, the effort that you have to make in order to put these atoms on these systems may be not worth the effort, but at least there is another system, and so probably, I mean, there gives you some other opportunities. Okay, so now what about spin models? So we have been also thinking that now these atoms close to these photonic crystals can give rise to very strong spin-spin interactions. And the basic idea is now not to put them close together. So let's now take a photonic crystal, let's drill the holes now separated by a wavelength in such a way that there are not CASIMIR-POLDER forces. Let's trap them somewhere there. And now the idea is that the atoms interact with each other by exchanging photons. So, so one atom, which is in an excited state, can emit a photon. This photon can propagate in your crystal, And if there is some other atom somewhere else that is in the ground state, can absorb this photon and go to the excited state. So altogether, what you have is a dipole-dipole interaction. So this kind of process gives rise to dipole-dipole interaction. However, this, of course, is very difficult to convince one photon to be in the fiber, or in this dielectric, and to come exactly to one atom, so probably it will go away. That's why you have to be a bit careful, and the basic idea is to do it with virtual photons. So since these are periodic systems, then the light propagating in these dielectric systems will have some band structure, so it's a kind of toy let's say, drawing of a band structure. And because you can have now that the transition frequency of your atoms is in the band gap, or it could be in the band, within the band. And so the idea is that you could use a laser with a frequency which is in the band. And well, I have to, well, maybe it's not very precise. But in any case, so you could use the band, as I'll show you in a second, in order to trap the atoms. And you could use now that the atom may exchange photons of this frequency in the band gap. So this would be a virtual transition. So an atom now can be in excited state and then virtually emit a photon in the band gap, and this is the one that is absorbed by the other atom. So this is a perturbative process, and this can give rise to some interaction. But the nice thing of these photonic crystals is that you can see here that if you look at the modes as a function of k, so you see that if you have some frequency here, you're getting closer and closer and closer to the h, the density of mode increases. So for a given interval of frequency, there are many k's here that have this frequency. So there are many modes for a very small frequency, so the density of mode is very big. So now, if your atoms exchange photons virtually, when you compute what is the dipole-dipole interaction, then you have to add to all the modes. So it can virtually be done through all the modes that are very close to this band h. And it turns out that if you do the calculation, since there are many modes there, you get huge numbers. And in fact, so we did, well, this is the process that I mentioned before. So, and this is, well, what I told you before. So you can do it now, the calculation with the real materials, I mean, with the real band structures. But at the end, we would do these computations with real band structures. So we get at the end some spin Hamiltonians of the form that I told you before. With this coefficient j, now can be something depending on the material that you use, can be as gigahertz dipole-dipole interactions. Okay, so in free space, the dipole-dipole interaction is of the order of 1 megahertz. If you just do it in free space, the the interactions of exchange, how spins can be flipped by exchange of photons, so you can increase 3 or 4 orders of magnitude just by using these photonic crystals. And in fact, now you get very long-range interactions. You can do the computations, and then you see that the interactions decay only like the log of 1 divided by the distance. So these are very extremely long interactions in the systems. Okay, so what I've said is that in principle, I mean, you have all these quantum simulations, and I was telling you some ways around how to get higher energy scales. So one was for Hubbard models, just by making some nanostructures with a very small period and trapping the atoms close in such a way that the distance when they have to hop is smaller, and therefore this increases the energy scales. This is a different way, also using a dielectric, but using the fact that you put some structure, then will be some band gap, and taking advantage of the band gap to induce dipole-dipole interactions among the atoms. And so this basically finishes my talk, but I wanted to just mention some other work that we have been doing related to this problem somehow. And so in our group during the last year, so first of all, that's a problem in what happens when you have an atom close to a one-dimensional photonic crystal. So it was shown many years ago by Young and Kwang that actually there may exist bound states of this atom and a photon. Or in other words, so you would think that you have a waveguide where the atoms can only propagate, and you put an atom and it's interacting, then you have an excited atom. The atom will emit a photon, and the photon will go away. So there is no bound state. However, it was shown that for these problems, indeed, the atom can bound a photon around it in such a way that you have a superposition of your excited state and zero photons in your fiber, plus 1 photon and the ground state, and the photon is around. So somehow, a way of interpreting that actually is that if you somehow eliminate the atom, you see that the atom is some imperfection for the photons that are moving in the waveguide. And so it can be thought as creating some potential for the waveguide. And if you compute it in some regime, then you see that this is an attractive potential. So you can have that one photon is bound in that potential because it's an attractive potential in one dimension. And so what we showed, actually analytically and so on, is that actually this is not only that you can have a single photon around it, but you can have many photons. You can bound many photons around it. I mean, you can prove it mathematically for some cases, but the interpretation is the same. So this impurity creates this potential for the photons, and this is attractive, so you can kind of Bose-condensate the photons there. So you can have many photons in that state, and this creates a bound state, so that's that you can show in this paper. On the other hand, the fact that you have strong couplings between atoms and these dielectric materials, because just shaping the structure will concentrate many modes around some frequency. So your atom has a transition frequency close where there are many modes, then there will be a big coupling. And this is what I told you before, that this relates to Purcell effects. So you can use this effect in order to create Fock state generators. So you could, in principle, have several atoms, excite all of them, like 20 atoms, you excite all of them, and since they are very coupled, then they will emit 20 photons, so you know that there are 20 photons coming out. Actually, that's not working like that, so naively, because one can very easily show that if you have 20 atoms, you create 20 photons, the photons that are coming out will not be single modes. So there will be 20 entangled modes in a very complicated state, so it will be useless, but we found a way to get not entangled state so that you really have a single mode with 20 photons inside. Another work is related to digital simulations, so high energy physics models. So as I told you before, one of the bottlenecks for this simulation for high energy physics model was these plaquette terms that you have to use fourth order perturbation theory in order to get to this magnetic energy in the lattice Hamiltonians. And one way around it that we were thinking is a bit sophisticated, but that's a way around it, and in principle you could think of now having, since you need different atoms, you need different fermions, you need fermions and bosons in order to simulate your high energy physics models, then they have probably to be trapped with different lasers. Okay, so they have to have some wavelengths for the fermions and some wavelengths for the bosons. But you have two different lasers trapping fermions and bosons. It means that they can be trapped independently. So in principle, you can move some of them up and some of them down. So you can be at a different distance. And then you can think now of moving them with respect to each other. And it turns out that if you start moving them in the appropriate way, then you get an effective interaction that can give rise to this four-body interaction without having to be perturbative. So in other words, you don't lose, let's say, strength in this model just by moving. So you may think a way that you have four particles and then you move one particle around that does some quantum gate, then this is equivalent to having a quantum gate among themselves. And that's what the other atoms are doing. And so in this way, principle, you can get better numbers for these plaquette terms in 2, and now we're doing it in 3 spatial dimensions for quantum simulation. And some other thing which is a bit unrelated, but we are very excited about this, is the possibility of using surface acoustic waves in solids to play photons in solid state qubits. So I mean, in atomic physics, so many of the experiments that are very interesting, like the one of Jacob, Rachel, and some, is that you can take atoms and then you can communicate, they can interact just by exchanging photons. So you can have one atom in a cavity here and another cavity here, and they can get entangled just by, because you send a photon that goes from an atom to another one. If you think about solid state qubits, for example, quantum dots, it's a bit harder. So you have a quantum dot here and another quantum dot here. So how can they communicate in such a way that they get entangled? And so in principle, you can send a current through. But so typically, the coherent length or the mean free path of an electron in some metal is very short. You can use also maybe chiral currents in some whole state. And I mean, this can get of the order of 100 micrometers, but actually there might be a better way of doing that could go up to something like centimeters, which is to use surface acoustic waves. So during the last few years, people have managed to create surface acoustic waves and to create build cavities for this surface acoustic wave, which have qualities of millions. So that's a really very long-lived phonons, let's say, moving the surface of a material, certain materials. And now these phonons, if you put a piezoelectric material, the fact that they oscillate in space, they make that this tension creates some electric fields that also oscillate, and they can couple now to charges. And so we have been thinking, so how now you can couple electrons in quantum dots, for example, using surface acoustic wave. And now we are thinking about even building, like say, the phononic lattices for electrons, where you can trap electrons and then build quantum simulators with electrons in materials. And so I'm working at that, and I think it's a very interesting topic as well. Okay, so anyway, so I think that I'm at the end, so let me summarize. So I've been talking about quantum simulation, and so as a way not only of doing wonderful experiments and learning about physics, but maybe as a technology to solve problems that people are interested in science. So we talk about material science, maybe in solid state physics, maybe in high energy physics. Of course, a big challenge and a very interesting area to expand would be quantum chemistry. So what could simulate chemistry problems and solve chemistry problems, like the molecular structure of some 100 atom molecule. With this system, this would be a really breakthrough. I mean, we don't know how to do this with the quantum simulator. We know how to do it to some extent with a quantum computer, but quantum computers are much harder to build, but maybe possible to do it with quantum simulators. These experiments are very challenging, and I don't have to tell you that. And in particular, the ones that I were talking about here on high energy and the ones on atoms on top of dielectric surfaces are really, really challenging and very difficult, and we are aware of that. But on the other hand, the papers that we wrote some years ago on cold atoms in optical lattices and trap ions and so on, they also looked very challenging at that time. And so the experimentalists managed to do some of them. So maybe at some point they also they're able to do some high energy physics models. And then I talk about something that is emerging during the last 2 or 3 years. It is this field of people call quantum nano-optics and quantum nanophotonics, in which you can combine atomic physics with nanophotonics, and then you see that there are things that you can do that maybe you cannot do with some of the systems. I thought about quantum simulation and about this photon generation, but it seems that that could give rise to interesting technologies. Okay, thank you for your attention.
My question is related to the Hubbard model.
Mm-hmm.
So people are interested in the phase structure of the Hubbard model, and there have been controversies like the existence or not existence of a superconducting phase in the Hubbard model. Now, in order to look at phases, you need to simulate large systems. So my question is, how large systems can you simulate? That's the first question. And the second question, have there been any conclusions on the structure of the Hubbard model?
Okay, so the first question is relatively simple. So you talk to the experts, they tell you that if they are able to do something like this is in 2 dimensions, where there is the controversy. You have 20 by 20 lattice. This would be enough. This would be, yeah, because you want to have more particles in the bulk than in the boundary in order to get rid of the boundary effects. And 20 by 20, I think that it's a good number already, that you have a lot of bulk physics there. That's a number, maybe it's 25 by 25, but I guess that's the order of magnitude. You don't have to go to something like 100 times 100. That's at least what I understand.
At least for classical simulations, you need to go to larger systems.
Well, for that systems, and this is the second part. So actually, for the Hubbard model in particular, there have been some breakthroughs during the last year or a couple of years, but now in some as a classical simulation. So people have used some techniques in order to solve this Hubbard model. And I mean, there are some conclusions related to that. I'm not sure to what extent they're seen. And so it's clear that there is superconductivity, a D-wave superconductivity phase where it's supposed to be. And one of the questions is whether there are some stripes or not stripes. And so what they find is that they see two solutions with an energy that is extremely small difference of energy, which have one stripes and the other one no stripes. And if I look at these simulations, then it seems that with a 20 times 20 lattice, so the numerics, 20 times 20 lattice would be enough in order to be able to draw conclusions.
But what is the status for quantum?
Okay, now the quantum simulations, I mean, the people who here know this better. I know that for a certain while, if you look at the phase diagram, there is temperature, and then there is the doping. And so you go to half link. This is very well understood. That's why experiments were there, in which as a function of the temperature, there's first a Mott transition and then a nil phase. And so people have already crossed the Mott transitions, but they have not got to the nil phase. So the temperature, as far as I know, is still too high in order to enter the the questionable region.
What is the best success story of quantum simulation with cold atoms so that we can advertise?
There are many, but okay, I'm very biased. So I have next to my door is Immanuel's Bloch lab. So I can tell you one of Immanuel's that I like very much. I mean, we could talk also about Christoph's one, but Immanuel Bloch just published a paper on Science in which he was able to simulate a many-body localized problem in 2 dimensions. So many-body localization is a problem that people are studying. It's very fashionable today, is that if you have disorder in your system and you have interactions at the same time, do you have localization, like Anderson localization? That is stable under interactions. And people have done it in 1 dimension. So in 1 dimension, you can go very, very far with numerical calculations. And then people have observed, and I think that is very well understood, that there is a phase transition somehow depending on the disorder that you have. Then there is localization or no localization. I mean, it's a bit complicated. But in 2 dimensions, nobody was able to compute that. Okay, so there were not predictions. And so you take a very simple model, which is like a kind of atoms tunneling and interacting with each other in 2 dimensions. And then you would like to see that if you start putting local disorders, so the local potential of these atoms, if you make more and more and more stronger, then whether the atoms will localize or not. And so what he observed very clearly in his experiment is he had a harmonic potential, and he started with half of the atoms, with the atoms in half of the potential. So he just blew away all the atoms in one part. And so he starts with all the atoms in the half of the harmonic potential in 2 dimensions, and he let them evolve. And then he looks at, as a function of time, whether the atoms now are completely distributed, or if they are more on the left side, such that they cannot move. And so he did, there is a Hamiltonian that you can write down, as far as I know, and I think that nobody has been able to simulate whether there would be a phase transition, meaning that for some value of the parameters, then all of a sudden it becomes localized. And his is very clear at phase transition. So he's able to solve a question that was posed before they did the experiment. So people didn't know whether there was a finite disordered transition for many-body localization. And so he was able to answer this question. Of course, what is interesting from the physics point of view is that now that we have this experiment, then you can start doing theory and trying maybe now to find the theory that would describe that. And I think that actually this is the most important thing that we have to learn from quantum simulation, not to solve Hubbard model, but to develop an understanding of these systems and maybe techniques to solve these systems that we don't have so far.
A provocative question. So the list of problems you mentioned reminds me very much of the list of problems Ken Wilson was mentioning to be solved by the normalization group. So there is one problem missing, Wilson was mentioning, which is turbulence. So can quantum simulation say something about the problems of turbulence?
Okay, turbulence are Navier-Stokes questions. You mean classical equations? I don't know about that. I don't know of any quantum algorithm or a quantum simulation that could solve it. What I can tell you is that there exist some quantum algorithms, not for this, but for a quantum computer, that can solve classical problems, statistical mechanic problems, with an exponential speed up. Okay, this has been shown. So there is a quantum algorithms, and in fact, we wrote a paper on that, of a quantum algorithm that if you give me a problem, Potts model in 3 dimensions something, if I had a quantum computer, I could solve it exponentially faster than you could simulate with Metropolis algorithm. No, I don't know if this can be applied to turbulence or not, but.
Okay, so let's thank